Okay, so today we're going to talk about section 7.4, which is division properties of exponents. So the last time we talked about multiplication properties, and now division properties are up next. And they kind of go hand in hand, but they're a little bit different, and we'll see how they are different here in just a little bit. And so what we first need to know is we need to know what we're going to do here. We're going to learn and use the properties of division for exponents to evaluate and simplify expressions. So once again, evaluate is for numbers, and simplifying is for algebraic expressions. Okay, so evaluate is when we're talking about numbers, and simplifying is when we're talking about variables and things like that. Okay, and so first, before we get started, we're going to do a little bit of an investigation about how these things work. So if we recall anything that we remember about, our exponents, what we're going to do is we're just going to kind of ignore this piece here for a second. Okay, so we're going to ignore this little section here, and we're going to say, okay, what is 3 to the 5th power? Well, you would tell me that this is equal to 3 times 3 times 3 times 3 times 3, right? And then if we did this, and we go back and we look at this one, and we kind of ignore the top. Now this time, we look at 3 to the 3rd power, and you will tell me that this is 3 times 3 times 3. Now, we know that what we can do is we can kind of split up this fraction, and we can say, well, there's a 3 on top, 3 on the bottom, and so we can kind of do some canceling here. And so what we're left with is 3 times 3, which is also 3 to the 2nd power. So look at the relationship. So if we remember what our bases are, okay, we have 3 as our base, so we have 3 as our base, that's the same. Now let's take a look at our exponents here. So our exponents are 5 and 3. So what we can do is we can look at this and say, okay, how are 5 and 3, how are those related in a way that'll give you 2? Okay, so think about that for a second. And how are those related that they could give you 2? Well, you can probably think of a couple different ways, but one of the easiest way is that if I take 5 minus 3, that gives me 2, right? Okay, so that starts to make some sense. So let's look at what possibly could be a rule. So now we come across this property, which we call the quotient or division, the quotient of powers property. So what this says is that the quotient of two non-zero powers, so obviously you can't have something 0 to the 0 power or anything like that, that have the same base. So when we're talking about all these properties, most of them, well, all of the properties at this point, deal with having the same base. They have to have the same base in order to do anything with these things. They have to have the same base. So they have the same base is equal, and that's equal to the same base. So whatever that base ends up being, we take that base and we raise it to what we would consider the difference of the exponents. Or in other words, what we're doing is this is subtracting. So when we say difference, we're talking about subtraction. And we always subtract top to bottom, so that all our subtraction problems look like this. If I was to use T and B, so it would be top minus the bottom. So top minus the bottom. I don't go bottom minus the top, I go top minus the bottom. Okay, and so let's take a look at some of these examples. So if we have the same base, okay, well we've got the same base, 2 and 2. So I use that base, and so I say 2, which is my base, raised to the power, the difference here, which is the top minus the bottom, which is 7 minus 2. And so what that ends up becoming is 2 to the power of 5. So what we're really doing is when we have the same base, all we have to do is subtract the exponents when we're dividing them. So with multiplication, what we did is we added them, and so remember we talked about addition and subtraction being opposites of each other, and then division and multiplication being opposites of each other. So if I add with multiplication, you would think that I would divide, or when I divide, I use subtraction. So let's look at when we have just numbers. So we have the same base, that's good. So we have x to the power of 4 minus 3, top minus the bottom, which ends up giving me x to the power of 1, or we can just simply say that that's x. And we're going to look at a couple more examples here. Okay, so now we're going to look at a few more in-depth examples. Now, what we want to make sure that we know is that we can always look at something that has the same base, and we can kind of, in a way, treat them as their own individual piece. And so what we can do is we can rearrange things so that they're in columns. So we have all our bases in a column, and these are all being multiplied together. So we have this one, we have this one, and then we have this one. Now, with multiplication, like we said before, is we can multiply in any order. And so what we can do is we can treat these as different things. And so what we can say is this is the same thing as saying 3 over 3 to the second power times 4 to the third power over 4 to the fourth power times 5 to the fifth power. So 5 to the fifth power divided by 5 to the third power. And so what we can do is we can then treat each one of these as an individual piece. And so what we can do is we can take our bases. So the first one I'm going to use in the first color. So we have 3 to the power of, well, what's the power up at the top? Well, remember we have that imaginary 1. So this is 1 minus 2. And then we take that and we multiply it by the next one, which our base is 4 to the 3 minus 4, top minus the bottom, and then multiply that by 5 to the power of 5 minus 3, which is going to give us the following. 3 to the negative 1 power times 4 to the negative 1 power times 5 to the power of 2. Now remember, this kind of goes back to what we've been talking about with exponents. Now with these, remember these are another fancy way of saying reciprocal. So we have 1 over 3 times 1 over 4 times 5 to the second power divided by 1 to make them all fractions. And we can multiply fractions by saying 5 to the second power over 3 times 4. And if we continue on, because we only want a single number, we can again say that this is 25 over 12 when we evaluate. And then that's it. If we look at our second example, now we're going to have to use some kind of creative manipulation here and use some of the examples that we know about before. So if I was to hide this piece up here and forget that this is any kind of division, do we know how to do this one here? Well, yeah, we use our multiplication or our product of a power. And so what we can do is we can say that this bottom piece here, so this is our bottom piece, really is the same thing as saying d to the second power times e to the second power. Because remember, we have to raise each one of these bases to a power. Now if we go back to our original numerator, we can just rewrite this because nothing changed. So d to the fourth power times e to the third power. And I can do exactly what I did on the other example and split this into two different problems. So my first problem is simply d to the fourth power over d to the second power. And then I can multiply that by e to the third power over e to the second power. And then when I use my quotient of a power, I can say that this is d to the 4 minus 2 times e to the 3 minus 2, which in this case leaves me with d to the second power times e to the first power. And then that's my answer. These aren't incredibly difficult, but what you need to make sure is that you take each problem and cut it into more manageable problems. So at first glance, this looked like a very large problem. But what I did is I put it into pieces and used the things that I knew in order to kind of make it smaller so that I could eventually, track it down. And so just a quick side note, I kind of have already talked about it before, but whenever we have fractions of numbers or anything else, what we can do is we can split these up, because remember, division is just a fancy way of multiplying, and so I can multiply in any order, and so I can split things up. So what I can really do is if I have a times c divided by b times d, really I can make this a over b times c over d. Or I could change the order and say c times a over b times d, and then I could get c over b times a over d. These will all eventually give you the same problem, because if I told you that a is equal to 2, c is equal to 3, b is equal to 4, and d is equal to 5, if I plug these numbers in, watch what happens. So if I do a times c is 2 times 3 over 4 times 5, and this is just the original problem here. What I'll end up getting is I'll get 6 over 20, which I'm not going to simplify this. And then if I use this one over here, this example, a over b, 2 over 4 times 3 over 5. Eventually what's going to happen when I multiply fractions, I multiply them straight across, and so I get 6 over 20. If I use this example here, same thing is going to happen. C over b times a over d is 6 over 20. So basically what I can do, as long as it's all multiplication, remember it has to be all multiplication, when I'm dividing things like that, I can split them up into different fractions however I need to, because what I really want to make sure is that what I'm finding is I can get a base, so 2 to the second power times 3 to the third power over, let's say, 2 to the, we'll say 3 to the second power times 2 to the first power. What I want to do is I want to be able to reorder these things. I don't want 2 over 3, because that's not going to be able to use my property, because I need the same base. And so if I manipulate these, I can rewrite this as saying 2 to the second power times 3 to the third power over 2 to the first power times 3 to the second power, and then I can use this idea of splitting fractions so that I can treat these as two different problems and then use my property that way. Okay, so now we're going to look at another property here, which is what we call a positive power of a quotient property. So basically what's going to happen here is we're going to have, if you look at these examples, we're going to have a fraction that's raised to a power of some sort. So the definition here is when a quotient is raised to a positive power, each, what we can say, term or base, because each one of these are going to come a base. So each term is raised to that power, and we kind of touched on this before. What I'm basically doing here is I'm taking this exponent and applying it to each one of these pieces. And so what I end up with is if I have 4/7 to the power of 2, remember, this is like saying 4 over 7 times 4 over 7, which is equal to 4 times 4 over 7 times 7, which is 4 squared over 7 squared. So instead of doing all of that, I can take a shortcut and just say that this is now going to become, so 4 over 7 to the second power becomes 4 to the second power over 7 to the second power. And since I know these numbers, I can just say this is 16 over 49. That's how we evaluate. But if we don't, what we would have is now we have an algebra example over here that is now starting to get a little bit more tricky. And so I need to kind of combine the properties that I knew about multiplication. And so each term, or each base, gets applied this. So I take this 4, apply it to the 3, then I apply it to the d squared, I apply it to the e, and I apply it to the f. So each one of those terms. Okay? So each one of those terms. So now all I have to do is I have to write this as 3 to the 4th power times d squared to the 4th power over e to the 4th power times f to the 4th power. Now the only thing that we want to make sure that we get rid of, because this isn't completely simplified because of this piece right here. Do we remember how to do this? What do we do when we have a power of a power? Well, all we have to do here is, if we remember, we multiply the exponents together. So 2 times 4 gives us the following. So we'll end up with this being equal to 3 to the 4th power times d to the 8th power over e to the 4th power times f to the 4th power. So what we're basically doing is, when we have a fraction of some sort, whether it's numbers or variables or a combination of those, I take that exponent that's on the outside and raise it to each term that's on the inside. And so we have to recognize what is a term, what is not a term, and then use our parentheses, these parentheses like in the d squared example, use these parentheses correctly so that we can see that this is d to the 2nd power to the 4th power, which we use our multiplication property that says we just multiply those exponents together. Now what we're going to look at is we're going to look at some more in-depth examples, and so we're going to combine all these properties and all these rules that we have of exponents. Okay, so when we have a fraction, so let's take a look at this, and let's just say again that this is one thing, this thing here, and this is another. Let's forget about all those numbers and all those exponents and everything like that. So we have green divided by red. So if I use my correct property, this says I take this 2 and apply it to each term, or each base. So we have this one, and it goes to here. So now what we have is, in a way, is we have green to the power of 2 divided by red to the power of 2. And then so now what I can do is I can just substitute in what green and red are. So if I erase this, let's look at what green is. Green really is 2 times x to the 3rd power. And so in parentheses I can write 2 times x to the 3rd power, and that's all being raised to the 2nd power. Now remember to include parentheses when we're substituting. And then red, well, red is the quantity, so we have to do 2 parentheses here. So xy to the power of 3. Now that's a little bit more intense. Okay? So now what we want to look at is we're going to look at, okay, how can we simplify this a little bit more? So let's look at just the top here. So if we look at just the top, okay, I use my property to say this is the product of a power, and so I use this to give it to each term here. And so I end up with 2 to the 2nd power times, remember this is multiplying together these two here, so x to the power of 6, not adding but multiplying. We only add when we have something that looks like this, x to the 3rd power times x to the 2nd power. It's the only time we add. And so now that's divided by something a little bit different now. And so what we have is we have the following. So now we have some value, and we're going to pretend that this doesn't exist for a second. So we have some number, we're going to call it red again, some number to the 3rd power to the 2nd power. And so I can use my rule there to say, well, all I have to do is multiply those exponents together, and so I get x times y to the power of 6. Okay? See how I did that? It's using that same rule, but what I'm doing is I'm just ignoring what's on the inside for a second and pretending that this is just x to the third power times, or x to the third power to the second power, and then x just happens to be x times y. And so if I look at this, okay, now I use my next rule and say I have to take this 6 and apply it to each one of these. So I raise those to the power. So if I start over, I have 2 to the second power times x to the 6th power on top. On the bottom now, I have x to the 6th power times y to the 6th power. That's using my multiplication properties. And now what I can do is I can rearrange these things like I did a couple of slides ago. So this is 2 to the second power times x to the 6th power divided by y to the 6th power times x to the 6th power. Split these up into two different problems. So can I simplify 2 to the second power divided by y to the 6th power? Well, no, that's got to stay the same. But x to the 6th power divided by x to the 6th power, well, if they're the same number, and we're subtracting this, because remember, this is going to stay the same, so 2 to the second power over y to the 6th power times x to the 6th over x to the 6th. Well, we're going to end up doing x to the 6th minus 6, which is going to be x to the 0 power, which also is 1. And so what we can do is we can just say get rid of this. That just becomes 1. So we have 2 to the second power over y to the 6th power times 1. Or when we simplify this, we get 4 divided by y to the power of 6. And that's it. Now it seems like a lot of work, and it is, but you can handle this with all the properties. So why don't you go ahead and try this one on your own. So go ahead and try that one on your own. And what you're going to end up finding is that you're going to end up finding the answer, which if I apply this, this is a little bit more straightforward. So a to the 5th power, b to the 4th power, to the 5th power, here and here. If I apply it to each one of those bases, what I get is I get a to the 5th power times, put it in a different color. So I'm going to get a to the 5th power times b to the 4th power to the 5th power divided by c to the 2nd power to the 5th power times d to the 3rd power to the 5th power. Now I use that same power of a power, and so I end up getting, and so I multiply those exponents together. So multiply, multiply, multiply. So when I do all that together, I get a to the 5th power times b to the 20, c to the 10th power times d to the 15th power. And now I don't have to worry about simplifying now because I don't have any variables that have the same base. Okay, so the last property that we have is the negative power of a quotient property, which works very similar to what the positive power of a quotient is, but just a little bit different working with this negative exponent. And so what we really need to do is we say when a quotient is raised to a negative power, take first the reciprocal, take the reciprocal of the base, which the base is going to end up being that fraction. So that's going to end up being the fraction that we have. Then each base or each term, so each term slash base is raised to the positive power. So basically what we're doing is we're using that negative exponent to take the reciprocal and then doing it the same way that we just did. So let's take a look at this. So if we take 3 over 4 to the negative 3 power, the negative implies reciprocal, and so we can say that this really is 4 over 3 to the power of 3. We can use that rule we just figured out about taking this exponent and applying it to each term. And so what I end up with here is I end up with 4 to the third power over 3 to the third power. Now I could have done the same property and said negative 3 to the third power, 4 to the negative third power, and got the same answer, but it requires a little bit more work. So if I ever see the negative exponent, immediately think reciprocal. And you're taking the reciprocal of everything that's on the inside of the parentheses. So when we move over to our next example, we say, okay, negative 2, take the reciprocal of whatever that base is or whatever that fraction is. So we take the reciprocal of this whole thing. So we just flip it upside down. And so we get y to the third power over 2 times x to the second power, and then that's all to the power of 2. Because now, once we did the reciprocal, that's what gets rid of the negative exponent. And so now what I can do is I can apply this exponent to each piece. Here, here, and here. Now remember, this is y to the third power to the second power. And so whenever we have a power of a power, we can just multiply those exponents. And so we get y to the power of 6 divided by 2 to the power of 2 times x, and then we take x to the second power to the second power, so x to the power of 2 to the power of 2. When we have power of a power, we multiply, and so we get x to the fourth. Now this isn't completely simplified yet because we know what 2 to the fourth power is, so we can just say that this is y to the sixth power over 4 times x to the fourth power. So really we're doing the same thing that we did just a minute ago, but what we're doing is we're first taking the reciprocal to get rid of that negative exponent. Okay, so this will really test what we know here. So like I said before, since we're using all multiplication, we can split this up into a couple different problems. The first problem I have here is these two things are actually being multiplied together. So we have this thing here, so this 3 over c to the second power is one piece, and then this whole piece is another thing. So let's first work with what we know. So if we look at 3 over c to the power of 2, okay, let's simplify this a little bit. And so what we end up getting here is we end up taking this 2, applying it to the 3, and applying it to the c. And so this is then equal to 3 to the second power over c to the second power, which isn't completely simplified yet, so I need to say, well, I know what 3 to the second power is, which is 9 over c squared. And that's it for that one. So let's take a look at this one now. Let's simplify this one. So we have 9 times d to the second power divided by 2 times c, all to the negative 3 power. Now what we just learned about is the negative exponent on the outside there. And so when we get that negative exponent, when we ever see the negative exponent, we want to take the reciprocal. So our new problem here now is 2 times c over 9 times d squared, all to the power of 3. Now, what you might see here is now we have a 9 here and a 9 here, and that's going to help us when we go a little bit further. So let's finish up this green problem here. Now I take this 3 here, that's on the outside. It's positive now because I took the reciprocal. Apply it to each term here. And so now this becomes 2 to the third power times c to the third power over 9 to the third power times d to the second power to the third power. Again, that's a power of a power. And so I can multiply those two exponents and get d to the power of 6. So now I have these two problems here. And so what I can do is I can take this piece and this piece, and really all I was doing here is I was multiplying them together. And so again, I can multiply these two fractions together and get 9 over c squared times 2 to the third power times c to the third power all over 9 to the third power times d to the sixth power. Now again, this is where it's going to come in handy to be able to multiply in any order and create fractions. Now since I'm multiplying these together, I can make this one big fraction. So this now becomes one big fraction. Because what we're doing is we're multiplying two fractions together, and it's still going to give me another fraction. Because really we're multiplying all these things together. So those two became one big piece. And so now I can reorder the numerator and reorder the denominator to get things how I want them. So the way that I do this is I want to get my numbers all together. So this is the way that I'm going to do this. I'm going to say, well, I want the 9s and a 9. I have a C and a C. These two things don't really make a difference right now, the 2 to the third power and the d to the sixth power. So what I'm going to do is I'm going to put those out front. I'm going to say this is now 2 to the third power over d to the sixth power times, or I can just make this a big fraction again, times, and then I'm going to do 9 to the first power, because remember this has that imaginary first power. This down here is 9 to the third power, and those are both multiplied by c to the third power, c to the second power. Okay, now I have all these columns, so I have a column, column, and a column, and I can treat those as three different problems. And so the three different problems that I have now are as follows. So I have d, or 2 to the third power over d to the sixth power times 9 to the first power over 9 to the third power times c to the third power over c to the second power. Okay. Now, what I can do here is I can start thinking about, okay, well, my method here for the quotient property is that I subtract the two together, right? But I can see that this one right here, that the top is a lot smaller than the bottom, correct? And so what it's going to do is it's going to give me a negative value. And so what's going to end up happening is I'm going to end up taking it to the bottom anyway. So what I can do is I can subtract the two exponents, and then whichever one is larger is where the ending value is going to reside. So when I do this, I end up getting 9 to the 1 minus 3, which gives me 9 to the negative 2, which is really 1 over 9 squared. But what I can do in this case is I can just keep it down there already. And so what ends up happening here is that with this, I know that this value is going to be negative. So I can just keep it down in the denominator so it's not negative. But what I'm going to do is I'm going to show it to you here. So I'm going to take this and I'm going to say 8, because 2 to the third power is 8, over d to the sixth power times 9 to the 1 minus 3 times c to the 3 minus 2. And so what's ending up happening here, I'm going to move this a little bit more. What's happening here is that I'm taking each one of these pieces and using that rule. I don't do anything with this one here, the 8 over d to the sixth power, because I can't. And so I get a fraction of 8 over d to the sixth power times, this is going to end up being 9 to the negative 2, which is really 1 over 9 squared, times c to the first power over 1. Okay, because this ends up being, let me write these in a different color. So I get 9 to the negative 2, and this is 9 to the, or c to the 1. And so c to the first power as a fraction, because I'm dealing with fractions, ends up being that. So if I combine all these things together, I get 8c to the first power, or just 8c. And then I end up on the bottom, I'm going to put the number out front, which is 9 to the second power, which is 81, times d to the sixth power. So I went from this gigantic thing here to this simple, straightforward answer of this. So if you want a little bit more extra help, go ahead and do the guided practice, because the guided practice will show you the steps. But then we'll talk about in class a little bit more about how to use these properties.